Hello, I'm Ron Mullison, Professor of Mechanical Engineering at Cal Poly in San Luis Obispo, California. And I have an experiment here which will verify the first law of thermodynamics by use of a friction bearing. I'll first describe the equipment, then we'll run the experiment and collect some data. I have a wood shaft supported on one end with a low friction bearing and supported on the other end with a friction bearing. Attached to the wood shaft is a pulley, and I have a nylon cord wound around the pulley. At the end of the nylon cord is a lead weight. I'll release this lead weight. It'll fall to the ground, rotating the shaft, rotating this bearing. The bearing will heat up, and I'll record the rise in temperature of that bearing. Let's look more closely at this friction bearing. There are two components, an inner portion and an outer portion. The inner portion of the friction bearing is connected to the wood shaft and rotates with the wood shaft. The outer portion of the friction bearing is connected to this wood block and it does not rotate. I have a thermocouple soldered to the outer portion of the friction bearing. I can adjust the friction with this clamp. There's a wing nut I will attach here later, and by adjusting that wing nut, I can load this friction bearing to the desired friction. I'll make two measurements when I run this experiment. One will be the rise in temperature of the friction bearing, and the other will be the rotational speed of the shaft. I want this rotational speed because I want the terminal velocity of the lead weight. By knowing the diameter of this pulley, the rotational speed of the shaft, I can get the velocity of that lead weight. I obtain the rotational speed of the shaft through the use of a homemade tachometer. On this end, I have two wires that make contact with a piece of aluminum tape that is just coming around now, and I'll rotate some more, it comes around again. And this is a homemade commutator. It's a make and break circuit with a 9-volt battery in the circuit connected to a strip chart recorder. And when I have that make and break, I get a series of peaks, which we'll see later. I'll measure the distance between those peaks. I know my chart speed, and accordingly, I can get the rotational speed of the shaft. We'll pause now, and we'll set up the experiment and then take some data. We're all set to perform the experiment. When I release this pulley, the shaft will rotate and the bearing will heat up. Okay, we're going to run this experiment again. This time we'll be looking at the strip chart recorder. The pen on the left is the commutator pen, giving us the rotational speed. We'll look at all the peaks. The pen on the right is connected to the thermocouple. So let's start the chart. And I'm releasing the weight now. And it just bound up. But we got a sense of what's happening. Stop the chart here. Well, let's take a close look at these traces. Here's the commutator pen. From one peak to a second peak represents one revolution of the shaft. So the shaft rotated 1, 2, 3, 4, 5, 6, 7 times before the bearing froze up. Now we'll look at the corresponding temperature of the bearing. As the shaft began to rotate, the temperature rose, and then when the bearing froze up, the temperature then cooled as the bearing cooled to the surroundings. I'll provide for you data for one run. The loss in gravitational potential energy of the lead weight will be equated to the rise of internal energy of the friction bearing. A ratio of these two energies will give us Joule's constant, 778 foot-pounds per BTU. We will also account for the kinetic energy of the weight before it impacts the ground, and the rotational kinetic energy of the pulley, and the heat loss into the wood block. When you reduce this data, you'll see how close you come to Joule's constant, which is 778 foot-pounds per BTU. Thank you.